Welcome to the deep dive. You've got a pile of articles, research, maybe your own notes, and you need to get smart, fast. Today, we're taking a deep dive into the world of version control, specifically one really powerful and I think often underestimated tool, Mercurial.
That's right. Our mission today really is to unpack the key concepts, maybe some surprising insights, and the practical ways you can use Mercurial. We're drawing heavily from Bryan O'Sullivan's excellent book, Mercurial, The Definitive Guide.
Yeah, think of this deep dive as your shortcut to understanding how you manage code, track changes, collaborate well, even when things get complicated. By the end, you should have a really clear grasp of what Mercurial is, why it's a top choice for, developers and teams, and how its clever internal workings actually protect your work. So let's dig in.
Okay, so at its heart, revision control, it tackles this universal problem, right? Managing multiple versions of stuff, we've all done it manually, saving files like V1, V2, final. It gets messy fast. And error-prone. Revision control tools automate all that, and they scale, from just you working alone up to huge projects with thousands of people.
And why Mercurial? There are lots of version control systems out there. What makes it stand out?
Well, the guide calls it a true field guide to distributed revision control. That distributed part is key. It highlights some unique properties. First off, it's remarkably easy to learn and use. People can get up and running in minutes. The command set is pretty uniform, very consistent.
Okay, easy to learn. And it's also supposed to be lightweight and fast. How does that actually feel when you're using it?
It feels nimble. Operations like creating change sets, making branches, transferring changes between repositories, even just checking history or status.
Yeah.
They're all blazing fast. It has this low cognitive overhead. It kind of stays out of your way, lets you focus on the actual work, the coding.
That sounds appealing, that simplicity. But does it really scale? Can it handle big, complex projects?
Oh, absolutely. The book points out it's used on projects with hundreds, even thousands of contributors, tens of thousands of files, hundreds of megs of source code. It scales. Plus, it's really customizable. It's built on Python. Its internals are clean. That makes it great for scripting, for building extensions. Teams can really tailor it.
Okay, let's compare it a bit. How does it stack up against something like, say, Subversion, which a lot of people are familiar with? What are the key differences?
Right. The biggest one is architecture. Subversion is centralized. Client-server. You're always talking to a central server for most operations. Mercurial. It's fully distributed. Every clone, every copy of the repository you have, it contains the entire history locally. This distributed nature usually gives it a big performance edge, like 2 to 6 times faster on common stuff. Subversion can really become a bottleneck, especially over the network. And merge tracking. Subversion added it, but when the source was written, it was still kind of new, bit complex, sometimes buggy.
But Subversion does have some strengths, right? I seem to recall something about large binary files.
Yeah, that's fair. Subversion's client-side space usage for big binaries tends to be constant, which is nice. And it has file locking, which can be genuinely useful for assets where you really only want one person editing at a time. Think like large design files or something. But crucially, Mercurial can import and export Subversion history. So you can try it out, test the waters without abandoning your existing history. That lowers the barrier to entry.
Okay, and what about CVS? That's even older, but some projects still use it.
Oh, CVS. Yeah, it's pretty old. Internally, it's kind of untidy. A major issue is its lack of atomic commits.
Atomic commits. What does that mean exactly?
Think of it like a database transaction, all or nothing. With an atomic commit, either all your changes across multiple files get saved together successfully, or none of them do. Your repository is always in a consistent state. CVS doesn't guarantee that. You could end up halfway through saving your changes, maybe across 3 files, and it fails on the 3rd one. The repository is left in a broken state. Breaks the build for everyone else. It's bad. Plus, its ideas about tags and branches are muddled, renaming files is handled poorly, almost no internal consistency checking. Generally, you wouldn't choose it for a new project today, though, again, Mercurial can import CVS history, which you inherit some of those limitations,
Gotcha. So the big takeaway is Mercurial, modern, fast, flexible, especially good for distributed teams, complex merging. It fixes a lot of old pain points. Okay, so you know why Mercurial. Let's get into the nuts and bolts. How do you actually use it? Starting with the core concept, the repository.
Right. In Mercurial, everything happens inside a repository. And it's really simple. It's just a directory, a special directory tree on your file system. Contains all your project files, plus their complete history. And because it's just a directory, you can rename it, delete it, move it around like any other folder.
And the main way to see that history is the hglog command.
Exactly. hglog is your window into the past. When you run it, you'll see key info. the change set ID, the user who made the change, the date, a summary. But there's something really crucial about that change set ID.
Oh, yeah. What's that?
Every change gets two IDs. There's a local revision number, like 2 or 5, simple, sequential. But there's also a permanent, unchanging hexadecimal string ID. Looks like, FEP8572004A0C, a long string of letters and numbers. The guide really hammers this point, that hex ID is the only safe way to talk about specific changes with other people, or in bug reports.
Why is that? Why isn't the simple number good enough?
Because the simple number, 5 for example, it's only unique in your copy of the repository. Yeah. If you and I both clone a project, and then we each pull different changes from different places, my revision 5 could be completely different from your revision 5. They depend entirely on the order changes arrived in our specific clone. The hex ID, though, it's like a universal fingerprint for that specific set of changes. It's permanent, global, unforgeable. Use the hex ID, everyone's looking at the same thing. Guaranteed.
Oh, okay. That's a critical distinction.
Yeah.
Makes sense. What else does HGlog show?
It also shows tags. Tags are just persistent, like human-readable names for specific revisions. You might tag v1.0, for example. There's also a special tag, tip, that always points to the very newest change in that branch or repository. If you want more detail, HGlog-eg cutch-evs adds the list of files changed and the full commit description. And HGlog-p, that shows the actual content changes, the diff. The guide calls this tremendously useful, and it really is, for understanding what changed or debugging.
Okay, so you've done some work, you want to save it, you use hgcommit that records your changes. But before you commit for the first time, you need to tell Mercurial who you are, right? How does that work?
Yeah, you need to set up your identity. Mercurial tries to guess, but it's much better to set it explicitly. The most reliable way is in a configuration file called .hgrc in your home directory. You add a line like e and then username, first name, last name, email that address at example.net. The guide even mentions Mercurial's web server can automatically obscure email addresses, which is nice for preventing spam if your repo is public. When you run a hgcommit, it usually pops open a text editor. You write your commit message there. Good practice is a concise first line. That's what shows up in the HGlog summary, followed by a more detailed explanation if needed. Oh, and any lines starting with HG are ignored. That's for Mercurial's internal use sometimes.
Got it. And if I just want to quickly see what the very latest change is?
HT tip, simple as that, shows you the most recent commit in your local repo.
Okay, so you've made changes, committed them locally. Now you want to share, collaborate. This is where the distributed nature really kicks in, right? How do you move changes around?
Right. The core commands here are hgpull and hgpush. hgpull brings changes into your repository from somewhere else, like hgpull.my-shared-repo. And hgpush sends changes from your repository to another one, like hgpush.central-server-repo. And before you do either, you can use hgincoming or hgoutgoing. These show you what changes would be pulled or pushed without actually doing it. Super helpful sanity check.
And Mercurial remembers where you originally got the code from.
Yes, it usually does. When you clone a repository, it saves the original location in your local .hghgrc file. Under paths, there's usually a default equal entry. So often you can just type hgpull or hgpush without specifying the path or URL again. It just knows. You can also set a different default push path if needed. And the really neat part, these commands work exactly the same way over a network. Just use a URL hdp.hdsh. Instead of a local file path. Mercurial handles the communication. It's seamless.
Okay, sharing changes is one thing. But what happens when people are working on different things at the same time? How do you bring that work together? Merging.
Right.
Merging. Yeah, fundamental for collaboration. Alice fixes a bug. Bob adds a feature.
Their work needs to combine. Or even just for yourself, maybe you work on a feature in isolation for a bit. The command is hgmerge. It takes the changes from another line of development and combines them with your current one into your working directory. It updates the files on disk, then you review the result, make sure it works, and then you commit the merge itself. That records the fact that these two lines of history came together.
What about conflicts? When Alice and Bob both change the exact same line of code.
Ah, conflicts.
Yeah.
Mercurial detects those.
Yeah.
It marks the conflicts in the affected files. It doesn't have its own built-in conflict resolution tool, but it's designed to call external graphical merge tools. Whatever you prefer, you can configure it. You set the hgmerge environment variable or configure it in your .hgrc.
Now, something I find really impressive is how Mercurial handles file management during merges, especially renames and copies. You mentioned a crucial benefit.
Yes, this is a huge differentiator from older systems. When you use commands like hgadd, hgremove, hgcopy, or hgrename, Mercurial doesn't just, do the file operation. It records the intent as metadata. And this leads to that crucial benefit. Changes follow copies and renames.
Explain that. What does changes follow copies mean in practice?
Okay, imagine you copy a file, utils.py to newutils.py, maybe as part of a refactor. You commit that copy. Meanwhile, your colleague finds a bug in the original utils.py and commits a fix for it. Later, when you pull their changes and merge, Mercurial is smart enough to realize that newutils.py is a copy of utils.py, so it automatically applies your colleague's bug fix to your renamed file, newutils.py. In older systems, that fix might just get lost, or you'd have a horrible merge conflict, or worse, the bug would reappear in your copied file without you realizing it. Mercurial prevents this. It tracks the history through the rename or copy.
Wow, okay, that sounds incredibly useful. Avoids a lot of potential headaches. What about trickier rename scenarios?
It handles them pretty well. If two people rename the same original file to different new names, Mercurial actually keeps both new files, warns you, and lets you sort it out manually. It doesn't just pick one and discard the other. If two people rename different source files to the same destination name, it uses its normal merging logic to help you combine them. There is one known tricky corner case, mentioned as issue 29 in the docs, involving merging a file and a directory that end up with the same name. But generally, it's very robust.
Okay, so merging is powerful, but how do you manage different long-running lines of work, like a stable release branch versus a bleeding-edge development branch?
That's exactly what named branches are for, organizing concurrent development, maintenance releases versus new features, that kind of thing. You use HG branch to see your current branch, or to create a new one by giving it a name. HG branches lists all the named branches in the repo. Just typing HG branch new feature doesn't do anything permanent yet. It's the commit you make after that command that records the branch name with the change set. Then you can switch between branches using HG update branch name. Jump back to the stable branch, make a bug fix, commit, then HG update new feature to get back to your feature work. Committing on a different branch creates a new head in the history, a separate line of development, which eventually you'll probably merge back.
This is all very practical, but let's peek under the hood a bit. What makes Mercurial so efficient and safe, and how it stores all this history?
Yeah, the internals are really clever. It starts with the rev log, the revision log. It doesn't store a full copy of every file for every change. That would be huge. Instead, it mostly stores deltas, just the differences needed to get from one version to the next. These deltas are usually tiny, like a fraction of a percent of the file size. And this works well for binary files too, not just text.
Storing deltas saves space, sure, but doesn't it make retrieving old versions slow? Having to apply potentially thousands of deltas?
Good question. Older systems had that problem. But Mercurial has a really neat innovation here. Periodically, instead of just adding another delta, it stores a new compressed snapshot of the entire file. Think of it like video compression, maybe. You have keyframes, the snapshots, and then changes between them, the deltas. When the accumulated size of deltas reaches a certain threshold, it just stores a fresh snapshot. This means reconstructing any version, no matter how old, is fast. You just jump to the nearest preceding snapshot and apply a few deltas. You never have to chain through thousands of them.
That's clever, like checkpoints. And what about data safety? What if my computer crashes while it's writing to the repository?
This is another area where it shines. Mercurial only ever appends data to its history files, the rev logs. It never modifies old data in place. And every write operation like a commit or pulling changes is part of an atomic transaction. It's all or nothing. If anything goes wrong midway, the whole transaction is rolled back. Nothing gets corrupted. This means readers, like another process doing an HG log, never see partially written, inconsistent data. It's incredibly robust against crashes or interruptions. Plus, every chunk of data stored has a strong cryptographic hash, like SHA-1, calculated for it. These hashes are used as the revision identifiers, those long hex strings. This makes it really hard to tamper with history, and it acts as an integrity check. If any data gets corrupted, say by a disk error, Mercurial will detect the hash mismatch and stop immediately, preventing further damage.
Okay, stopping immediately if something's wrong is good. Now, what about the working directory, the actual files I edit? How does Mercurial manage that?
Right. The working directory is basically a snapshot of the project's files taken from one specific change set in the history. Mercurial keeps track of the state of this working directory in a special file inside the .hg directory called dirstate. This dirstate file is like Mercurial's brain for your working copy. It knows which change set you're currently based on, updated to. It lists all the files Mercurial is tracking, and it stores information like modification times and file sizes. It uses that info to very quickly detect which files you've changed since your last commit or update. It also has slots to remember the parents of the working directory, usually just one, but two when you're in the middle of a merge.
And you mentioned performance earlier. Does the dir state help with that too?
Yes, definitely. Mercurial really prioritizes avoiding disk seeks because seeks are slow. Having all that working directory state information consolidated in a single dir state file helps avoid lots of seeking around. Also, when you clone a repository locally on the same file system, Mercurial often uses hard links for the files initially. This is like a copy on write strategy. It doesn't actually copy the file data until you modify it. The guide puts it bluntly: storage is cheap, and this method gives the highest performance.
Okay, this focus on performance and robustness leads to something pretty significant for teams: concurrent access.
It's a huge win, yeah. Because of the append-only design in atomic transactions, Mercurial never needs to lock the repository for read operations. Even if one process is writing, like pushing changes, any number of other processes can simultaneously read from the repository, like polling or browsing history, without being blocked or seeing inconsistent data. This massively boosts scalability, especially for build servers, web interfaces, or large teams all accessing a central repo. It also simplifies permissions. Often, users only need read permission on a shared repository to be able to clone it or pull updates. Only pushing requires write access. Write operations are locked, of course, to prevent chaos, but reads are lock-free.
And compression. We talked about deltas and snapshots, but are there other tricks?
There are. One small thing. It only stores the compressed version of a delta or snapshot if it's actually smaller than the uncompressed version. Seems obvious, but it avoids making already compressed files, like JPEGs or ZDPs, slightly larger, which some systems might do. But the really clever bit is network recompression, especially over HTTP. When sending a bundle of changes over HTTP, Mercurial can actually uncompress the individual delta snapshots, then recompress the entire stream of data using a more powerful algorithm, typically related to BitZip2, Burroughs-Wheeler. This algorithm is better at finding redundancy across the whole bundle, not just within single files. So even if the individual files are already compressed, compressing the whole stream together often results in significantly fewer bytes transferred over the network, which means faster pulls and pushes. Over SSH, it usually lets SSH handle the compression itself.
Okay, Mercurial sounds robust, but mistakes happen. We all make them. What tools does it give you for finding and fixing things when they go wrong?
Good question. Let's start with local mistakes before you've shared anything. If you've just modified some files, maybe deleted one by accident, but you haven't committed yet, hgrevert is your best friend. It's really versatile. It basically restores selected files or the whole directory back to how they were in the parent revision, usually the last commit. It undoes your local modifications. If you accidentally hg added a file, hgrevert will unmark it as added, but leaves the file there. If you manually deleted a file, Mercurial sees it's missing. hgrevert brings it back. If you hg removed a file, hgrevert restores it and unmarks it as removed. It cleans up local messes.
Okay, that's for uncommitted changes. What if I just did a commit or maybe a pull and I immediately realized it was a mistake?
For that, there's hg rollback. This command undoes the last transaction that modified the repository's history. That could be your last hg commit. Or, very usefully, it could be your last hg pull, a common scenario. You accidentally hg pull from the wrong URL. Oops.hgpull usually tells you where it pulled from. You see the mistake, you type hg rollback, and poof, all the change sets you just pulled are gone, as if it never happened. It works because Mercurial groups all the change sets from a single pull into one transaction. But there's a big caveat. hg rollback only works if you haven't pushed those changes anywhere else. Once they're out in the wild, rolling back locally doesn't help, and you can only roll back the very last transaction, just once.
So if the bad change has been committed and maybe even pushed, I can't just erase it. What do I do then?
You use hg backout. This is the standard way to reverse a committed change that might already be shared. hg backout doesn't rewrite history or delete the bad commit. Instead, it creates a new commit that precisely reverses the effects of the bad one. It looks at the changes made in the commit you want to back out, calculates the inverse changes needed to undo them, applies those inverse changes to your working directory, and then prompts you to commit this new reversal change set. If the commit you're backing out isn't the absolute latest one, the tip, this might create a new head, which you'd then probably merge. The really nice thing, as the guide points out, is that hg backout uses Mercurial's powerful merge logic internally. This makes it much more reliable than just trying to apply a reversed patch, especially for older changes where the surrounding code might have changed a lot. Patch reverse often fails in those cases due to broken context. hg backout is smarter.
Okay, backout handles reversing known bad commits. But what if a bug crept in somewhere in the last, say, 500 commits, and I have no idea which one caused it? Hunting that down sounds painful.
It can be incredibly painful manually. That's where bisect comes in. It's like magic for finding the commit that introduced a bug. Instead of you manually checking out commit after commit, update test, update test, bisect automates a binary search through your history.
Binary search, how does that work on code history?
You start by telling it a known good commit, where the bug didn't exist, and a known bad commit, where it does exist, usually tip. bisect then checks out a commit roughly halfway between good and bad. You then test that version. Does the bug exist here? You tell Mercurial.bisect good if it works, or bisect bad if it's broken. Based on your answer, Mercurial eliminates half the remaining range of commits. It checks out a new commit in the middle of the remaining range, and you repeat that test, report good or bad. Each test cuts the search space in half. So finding a bug in, say, 10,000 changesets doesn't take 10,000 tests. It takes about log base 2 of 10,000, which is maybe 14 tests. The guide contrasts this. Manual testing at 10 min tests for 10K changesets could take 35 days. bisect turns that into less than 3 hours. It's amazing. It finds the first bad revision that introduced the regression.
That is a massive time saver. Any tips for using bisect?
Yeah, a few. Use bisect reset to start over or when you're done. Be consistent with your good-bad reports. If you land on a revision you can't even test, maybe it doesn't compile or some other unrelated bug interferes, use bisect skip. It will just try a different nearby commit. It's also smart enough to handle merges and branches correctly, pruning whole branches if necessary.
Okay, we've covered core usage, sharing, fixing mistakes. Let's talk about tailoring Mercurial and different ways teams collaborate. It sounds like Mercurial is pretty flexible here.
Hugely flexible. Because it's distributed, it doesn't force one single workflow on you. The simplest model is maybe a single central repository. This feels familiar to people coming from, say, Subversion. Everyone clones from it, pulls updates from it, pushes their completed work back to it. Even in this model, though, developers can still pull changes directly from each other's clones to test things out before pushing to the central repo. Often you'd use SSH for push access and maybe HTTP for read-only access, pull clone.
What about bigger projects, more complex workflows?
Then you start seeing things like multiple branches, often represented by multiple central repositories. Maybe one repo for the stable release branch, another for the main development branch. Bug fixes might flow from stable to main via polls and merges, but new features stay isolated in main until release, or feature branches. Teams work on new features in complete isolation, maybe in their own clones or a dedicated feature repo, then merge back to a master or main branch when the feature is done and tested. There's also the release train model. Features aim to get merged into the main line by a certain cutoff date for the next scheduled release. If a feature isn't ready, it misses the train. The team then merges the new release back into their feature branch and aims for the next train.
You mentioned the Linux kernel model earlier, too. Pull only, based on reputation.
Yeah, that one's fascinating. It's very decentralized, almost looks chaotic from the outside, but it works incredibly well. It's a hierarchy based on trust and reputation. Linus Torvald sits at the top. He only pulls changes from a small number of highly trusted lieutenants. Those lieutenants, in turn, pull changes from maintainers of specific subsystems, like networking or file systems. Those subsystem maintainers pull changes from individual developers or smaller groups. Crucially, it's pull only. You don't push your changes onto someone else's repository. You make your changes available, and you ask the maintainer above you to pull them if they think they're good enough. You build reputation by submitting clean, working code.
Interesting. So, technically, how do you actually share repositories for these workflows?
Several ways. For quick, informal sharing on a trusted network, hgserve is super easy. You just run hgserve inside your repository directory. It starts a simple, lightweight web server right there on your machine. It'll print out a URL like http.my-laptop.local-800. Anyone on your network can then pull from that URL. It's usually read-only and unauthenticated by default, so not for sensitive stuff or untrusted environments, but great for quick peer-to-peer sharing. Use hgserve-v to easily see the URL.
Okay, hgserve for quick sharing. What about more permanent, secure setups?
Then you'll typically use SSH or HTTP served by a proper web server. For SSH, you use URLs like sweltis.user at host.portpath-to-repo. The path can be relative to the user's home directory or an absolute path if you use MIGAR. On the client side, you need an SSH client, like OpenSSH on Linux Mac or TortoiseHG often bundles PuTTY tools on Windows. It's highly recommended to set up SSH key pairs.
Shkeen or Putijin, so you don't have to type your password constantly. Protect your private key with a strong passphrase. You can use authentication agents like Sosh Agent Unix or Pagent Windows to cache your decrypted key in memory, saving you from typing the passphrase repeatedly, though that's a slight security trade-off. On the server side, you need the SSH daemon running, firewall allowing connections, usually port 22, correct file permissions on .sj directories and authorized keys files. And importantly, the SDG command needs to be in the executing user's path on the server.
Right, standard SSH setup hurdles. And stowing over HTTP with a real web server, like Apache or LightTPD.
Yeah, that's the common way to provide permanent, often public or semi-public, access. Mercurial provides CGI scripts, .hgweb.cgi for serving a single repository, and hgwebdir.cgi for serving multiple repositories from a directory structure. The guide is quite honest here, saying configuring web servers is often complex, fiddly, and highly system-dependent. Expect to consult web server docs and look at error logs. It actually recommends LightTPD is potentially easier to configure than Apache for this. Basic checklist.webserver installed and running. CGI execution enabled for the directory where you put the scripts. Script is executable, shaft 755. For hgweb.cgi, single repo, you usually just need to edit the script to set the path to your repository. For hgwebdir.cgi, multiple repos, it uses an external config file, hgweb.config. In there, you use collections to point at directories containing repositories you want to serve, mapping file system paths to URL paths, or paths to list specific repositories explicitly. Be careful not to create duplicate URL paths.
And can you customize how those web interfaces look or behave?
Yes, there are options you can set, either in the hgweb.config file or in the Mercurial configuration file.hrc of the user the web server runs as. That last part is important. The CGI script runs as the web server user, like www.data or Apache, not as you. Options let you enable downloading snapshots, allow archive, control if pulling cloning over HTTP is allowed, allow pull, set contact info, descriptions, choose different visual styles or templates, etc.
Okay, that covers sharing. Now, automation and policy enforcement. This sounds like hooks.
Exactly. Hooks are scripts or code snippets that Mercurial runs automatically at specific points in its workflow, like before commit happens, pre-commit, after commit is finalized, commit before changes from a pull are added, pre-dex and change group, after you push changes outgoing, and so on.
And these hooks, do they get shared when I clone a repository?
No. And this is a critical security principle. Hooks are not revision controlled and do not propagate with clones or pulls. Imagine if they did. Someone could put a malicious script in a hook, you pull their changes, and the hook runs automatically on your machine. Bad news. So hooks are local configuration. If a project relies on certain hooks, the example for code style checks, that needs to be documented so collaborators can set them up themselves. Users can always override or disable hooks in their local configuration.
So if hooks are local, how do you enforce critical policies centrally, like commits pushed to the main server must pass all tests?
For non-negotiable rules like that, you set up the hook on the server side, specifically a pre-transaction hook like predix and change group. This hook runs on the server before it accepts the incoming change sets from a push. The hook can then examine the incoming change sets, maybe run tests, check commit messages, verify permissions, whatever your policy requires. If the hook script exits successfully, status 0, the push is accepted. If it exits with an error, non-zero status, Mercurial rejects the push and the changes never land in the canonical server repository. This is how you enforce policy reliably.
How do you actually write these hooks?
Two main ways. External hooks are just executable scripts, shell scripts, Python scripts, anything. Mercurial passes information to them via environment variables like hgno, hgurl. They're easy to write, don't need deep Mercurial API knowledge. Just exit 0 for success, non-zero for failure. They can be a bit slower as they involve starting a new process. In-process hooks are Python functions defined within Mercurial's configuration files. These run directly inside the HG process, so they're faster and have full access to Mercurial's internal APIs. Better for complex logic or performance-critical checks.
Can you give some examples of practical hooks?
Sure. A common predix and commit hook might check if the commit message is meaningful, AG, not empty or shorter than 10 characters. A more complex Python predix and commit hook could parse the diff of the changes being committed and check for things like trailing whitespace on newly added lines, failing the commit if found. A predix and change group hook on a server is often used for access control. The built-in ACL hook lets you define in the server's config file, akil.allow, akil.deny, which remote users, identified by their push authentication, usually SSH key or username, are allowed to push changes affecting specific files or directories within the repository. It checks the pusher's identity, not the original committer of the change sets. Another example, An incoming hook runs after change sets are added locally, for example, after a poll, could integrate with a bug tracker like Bugzilla. If a commit message mentions fixes bug 13345, the hook could parse that ID and automatically add a comment to Bugzilla issue 13345, linking back to the change set. The book gives a detailed example for this.
Wow, hooks sound incredibly powerful for customizing workflows.
They really are. And hooks can even tell how changes arrived using environment variables like hgsource, was it a poll, push, unbundle, and hgurl, where did they come from, allowing for even more tailored logic.
Okay, shifting gears slightly, customizing output. You mentioned hglogrp is useful. Can you customize the output of commands like log even further?
Yes, using templates and styles. Mercurial has a powerful templating system that lets you control exactly how commands like hglog, hincoming, houtgoing, httip, and even the web interface display information. A basic template is just text mixed with keywords and curly braces. For example, a template like changeset, node, and summary, date signal would format log entries nicely. End is a new line.
So you can pick and choose which pieces of information to show, like the hex ID, node, the author.
Exactly. Common keywords include author, branches, date as a raw timestamp plus offset,
Yes.
desk, full description, files, list of changed files, filiads, filadels, node, the full 40-char hex ID, parents, rev, the local revision number, tags, and more. What makes it really flexible are filters. You can pipe the output of a keyword through filters using a GAC, like data-state formats the date nicely. Node short gives you a shorter 12-character version of the hex ID. Date strip fill 68 tab indent would strip leading trailing white space from the description, wrap it to 68 columns, and then indent the wrapped lines. You can chain filters together.
And can you save these custom formats so you don't have to type them out every time?
Yep, that's what styles are for. You define your template in your .hgrc file, give it a name like templates mylog, and then you can tell Mercurial to use that style by default, ustyle mylog, or specify it on the command line, aglog style mylog. Mercurial even comes with some built-in styles, and the guide shows how you could create a style file to make hglog output look almost identical to svnlog, which can help people transitioning.
All right, one more major area from the guide, managing patches, especially with Mercurial queues or MQ. What's that all about?
MQ is basically a sophisticated patch management system built on top of Mercurial. It's bundled as an extension. It's really powerful for workflows where you need to manage sequences of changes that aren't yet finalized or integrated. It introduces the idea of a patch stack. You work with patches, which are essentially managed diff files. New my-patch.patch creates a new empty patch file and puts it conceptually on top of a stack of applied patches. Series lists all the patches MQ knows about in the order they should be applied. Complied lists only the patches that are currently active whose changes are actually present in your working directory right now. You can pop a patch, which removes its changes from the working directory and backs up the patch file, moving you down the stack. The patch is still known, just not applied. And qpush reapplies the next available patch from the series file, moving you up the stack.
So there's this difference between a patch MQ knows about and a patch that's currently applied and affecting your files. And it uses standard patches underneath.
Exactly. The key concept is that applied-unapplied distinction. Figure 12:1 in the book has a good diagram of this stack idea. And yes, under the hood, MQ uses standard patch files, like you generate with diffview, and unapplies them using the GNU patch command. Understanding patch headers and things like the strip count, NAGE1, can sometimes be helpful if things go wrong, but usually MQ handles it. You can refer to patches by their name, pop my-patch.patch, by relative offset from the top, pop tip2, or using special names quace, the underlying Mercurial commit the stack is based on, and kip, the topmost applied patch. Commands that take a changeset ID often also accept an applied patch name.
How do people use this in practice, especially on big projects?
For organizing, you can put patches into subdirectories. MQ manages the paths. But really crucial for large projects is carefully managing the series file. The guide suggests organizing the series file into logical sections using comments. The order is vital. A typical setup might be 1. Accepted. Patches already accepted upstream. Put these first for stability. Treat as read-only. 2. Rework. Patches submitted but need changes based on feedback. 3. Pending. Patches finished, ready to submit but haven't been sent yet. 4. In progress. Patches you're actively working on right now, usually at the top. 5. Backport. Patches adapting newer code to run on older versions, e.g. older kernels, often need to be applied last. 6. Do not ship. Internal patches, debugging aids, never intended for upstream.
That structure sounds useful. Does MQ offer ways to manage applying these different groups?
Yes, using guards. You can associate flags, guards, with patches in the series file.
like plus accepted, plus devil, plus needs rework, plus Linux 2.6.28. Then you can use commands like select accepted to tell MQ you're only interested in patches without the accepted guard, or collect Linux 2.6.28 to activate only patches with that specific version guard. QPushGuard can then apply patches conditionally based on the active guards. This gives you incredible flexibility to construct different versions of the source tree. For example, apply everything except accepted patches, or apply only the patches relevant for this specific kernel version. For backporting, the aim is often to make the patch look native to the older code, using guards to avoid cluttering the main code with #ifdefs.
And tracking changes to the patches themselves, since they evolve.
Good point. Since the .diff files are just text files, though usually not checked into Mercurial itself, they live in the .hg patches directory, standard diff tools work. But the guide recommends the xdiff extension combined with a tool like interdiff. Interdiff is specifically designed to show a diff of diffs. It compares two patch files and shows you how the patch itself changed between versions. Much more meaningful than just diffing the two patch files line by line.
Last thing on patches, sending them out for review.
For workflows involving email review or submitting to gatekeepers who prefer patches, the patch bomb extension, often just called email, is the tool. HG email takes a range of revisions and formats them as patch emails, typically one email per change set. Always use hd email-n or dry run first. This shows you exactly what emails it would send without actually sending them. Prevents embarrassing mistakes. It has options to customize the subject, sender, send a binary bundle instead of text diffs, -b, send plain diffs without explanation, include diffstat summaries, and more.
Okay, one final major topic, migration. People might be using Subversion or CVS or Git now. How do they get their history into Mercurial?
Mercurial has a built-in extension called Convert, specifically for this. It's very powerful. It supports importing from Subversion, CVS, Git, Darks, Bazaar, Monotone, GNU Arch, and even from Mercurial itself, which can be useful for repository manipulation. A key feature is incremental conversion. You run hg convert once to get the bulk of the history. Later, if more changes were made in the old repository, you can run hg convert again on the same destination Mercurial repo, and it will intelligently import only the new revisions it hasn't seen before. It uses a metadata file .htchap to track this.
Does it handle things like Subversion's standard trunk tags branches layout?
Yes, it usually detects that standard layout automatically. By default, it might convert SVN branches and tags into Mercurial named branches. Or you can configure it to just import trunk for a simpler linear history, ignoring the SVN branch as tag structure if you prefer. You can also use file maps during conversion. This is a tag file where you can give convert instructions like include path to keep, exclude path to ignore, or rename old path new path. This lets you clean up or restructure the project's layout as part of the conversion history.
That sounds useful for cleaning house during a migration. Any performance tips for huge Subversion repos? Conversion can be slow over the network, right?
Definitely. If you have a really large Subversion repository, especially if you expect to run the conversion multiple times while tweaking parameters, network access is the killer. The recommended approach is to first use svsync, a Subversion tool, to create a local mirror of the remote SVN repository on your machine. Then run hg-convert against that local SVN mirror. Accessing the local mirror is thousands of times faster than going over the network for every single revision check during conversion. Makes experimenting with conversion options feasible.
Good tip. And just to reiterate, the core philosophical difference to keep in mind when moving from something like Subversion.
It boils down to centralized versus distributed. Subversion. Client talks to server for many things. History lives on the server primarily. Mercurial, distributed. Full history is local. Network is only for syncing between complete repositories. Also, Subversion's branching model is less integrated. Mercurial treats the repository itself as the unit of branching and merging, making those operations feel much more natural and core to the tool.
Okay. Any final quick tips for people just starting out with Mercurial?
Yeah, a couple of small handy ones. To see the diff for just a single revision, without checking it out, you can use hg export rev or hg log hr rev sp. Avoid typing the ID twice like hg diff match rred1-rrev, also hg status. By default, it shows paths relative to the repository root. If you want paths relative to your current directory within the repo, just give it a file or directory name, hg status, src, or use backticks like hg status, the obj root on Unix-like shells to get paths relative to where you are.
So wrapping this all up, we've covered a lot of ground here.
We really have. We've navigated through Mercurial's landscape, pulling out, I think, the key ideas about its design, how it works day to day, and how it helps you manage complex projects, collaborate effectively. From the robust way it stores data, the smart merging, the flexible workflows, it's really built for modern development challenges.
Yeah, and if this deep dive has sparked your interest, definitely check out Mercurial, the definitive guide itself, or the official online documentation, which is also excellent. Like any tool, the best way to really learn it is to use it. Try it out on a small project.
Right. And maybe a final thought, connecting back to that house martin on the book's cover, it's a bird that adapted, thrived by using human structures for its nests. So the question for you is, how can embracing this distributed way of working, the kind Mercurial enables that mix of individual autonomy and strong, reliable collaboration? How can that help you adapt? How can it help you build more resilient, more innovative projects, regardless of how your team is structured or where everyone is located?